Hello everybody, my name is Nino, and in this video I would like to describe to you my considerations regarding artificial intelligence, and I hope that they will be interesting and entertaining to you. In order to have a more physical demonstration, I wired up an Arduino. Say hi to people, please. Yeah, and I'm going to show you some experiments which show how my theories can be applied. You will find further details on my website, which is at sites.google.com/site/logical triangulation. There you will find my theory of logical triangulation, which is a kind of reasoning mechanism for an artificial intelligence, my theory regarding fragmentation sets, which is a simplified version of the first theory and handles patterns in a less precise but faster way, and of course the wiring schemes and the descriptions of how to handle the Arduino. Without further ado, let us come to the first question. What is intelligence anyway? On this it depends what an artificial intelligence might be. So I'm saying you're having an entity, let's call it the system. The system is going to receive some kind of input, and it is going to output some kind of response. That response must be intelligent. That is a little tautological, I understand, but it really only matters what you, the human, believes is intelligent. No other measure of intelligence is interesting. This simple definition has the advantage that what is intelligent is in fact measurable. You can say, is it good or is it bad? Now, for an intelligent reply to be output, the system will need to apply some kind of reasoning. After all, that's why you would call it an artificial intelligence. I believe that at the core of all reasoning lie two simple processes. First, from input or thoughts to find analogies, and second, to use those analogies somehow. So if you say that a black shape corresponds always to a white shape, and again a black shape corresponds to a fitting white shape, then if you get a new black shape, you'll find again the corresponding white shape easily. That is, here you find what is the common rule and finding how to apply it in an analogous manner to new patterns. And when a new pattern comes, you use that rule. How you do this doesn't, by the way, matter at all. It's just important that this evaluation is done in general. You may use for that anything you see fit, from neural networks to Bayesian reasoning to vector spaces or my own proposals of logical triangulation or fragmentation sets. It doesn't matter as long as you are able to grasp analogies and use analogies. Now, how is an analogy really used? Let me show you a little sketch regarding that. Now, suppose that you know that there is a wolf and that you should better run away from it, right? You know how to escape from a wolf. And then you actually are in the current situation that a bear is attacking you. Then you recognize that the bear is also fluffy, just like the wolf. It is also roaring, just like the wolf, and it attacks you. So you are saying these are analogous, and you transfer the one behavior to the current situation and run away from the bear just as well, or hide or do whatever. But you escape from the wolf, find out that the bear is analogous to the wolf, and use the conclusion which you drew by analogy. Now, in an abstract way, we can therefore formalize what you do with analogies in the following way. You perceive some kind of information, like for instance my beautiful bear here. Then you are evaluating somehow that situation internally, and then you are acting on that evaluation. Again, what evaluation mechanism precisely is used is not of much interest here. The point is you must somehow be able to recognize analogies and use them. So you're having perception, evaluation, and action. The next question is, well, how do you learn even a proper response? How do you know that you should run away from wolves? Well, you are simply going to observe what the outer world does. You see, wolves are chasing people, some of them are less fortunate, and you are going to see that and learn that that is the general behavior. You see that people run away from wolves, and that is exactly what you are going to do. Later on, I'm going to show you how this can be formalized. In fact, you can call that a process of imitation. You see how others do, you learn that that's an appropriate action, and you use it yourself. Now, the next point is, having established this general learning mechanism, how exactly does the system then learn? You say, there's a system and it is being somehow challenged by the human with some kind of challenge. Let's say he challenges the system with a shape. What is the system going to do? It is going to reply, but it can only guess its reply. There is no way for the system to establish that that reply is correct. How is it going to guess that reply? Broadly speaking, you can say that it knows that there are some kind of challenges and it knows that there are some kind of proper replies. So when it sees the challenge, it is going to say, well, isn't there something that I know how to reply on a triangle? Ah, right, I reply with a square. But that is a guess. However, how do you get to know such a challenge-reply pair? Well, it can be learned from the way the human challenges the system. Because the human is now going to receive that square. And let us say that he answers with some shape with 5 corners, right? So it learns, the system learns, that something like that can be answered by a thing like this. And there you have a new challenge-response pair, which has been learned through this interaction. In other words, you can say that there is a circular interaction between a system and a human, where each time the human challenges the system guesses a reply to the human. And each time the human now replies to the system's response, the system can learn that as a new challenge-response pair. So when the system has told that as an answer to this, the system can learn this new pair. Obviously, that's not the whole story. And you can say that there should be some further evaluation happening based on the challenge-response pairs which have been learned. But the general idea still remains: the more situation the system knows how to reply to, the smarter will it become. And you can therefore say that the system can increase its reasoning capacity by having the ability to memorize more challenge-response pairs. And in a typical interaction, like for instance here, I am only showing what has been learned, the system really can learn a certain set of proper challenges leading to some responses. And when in future, let's say it receives some circle as input, it will know, wait, well, then I will reply with a corner pointing to a side. This is a little bit automatic, you might say. So, is this really everything? The answer is no. In the beginning, we said the system should really be able to reason on the information it receives. So, what it might do? Well, let's say that it has just learned a new challenge-reply pair. It has learned that some kind of triangle triggers some kind of square. It may then refine that concept to say, a triangle in an abstract way triggers a square in an abstract way. And besides, it might say, from this it can derive analogies. It says that one shape with one corner less is going to trigger another shape which has one corner more. And then the system can learn how to handle further shapes for which it has not directly observed the challenge-response pair, but that is what the internal reasoning mechanism will do. Again, no matter what reasoning mechanism, it just must be able to derive analogies. Now, some people in the past have told me, but what happens when a human really replies? He really replies on a situation. He doesn't just tell you triangle or square. He tells them in some kind of situation. But you realize that situation is the same as if you say there is some kind of context. And real context is nothing else but a kind of history. So when you're asked, would you like a cup of tea and you feel way too hot, you may decline. If you're asked, would you like a cup of tea in the winter, you will accept. But in both cases, you're not just asked, would you like a cup of tea? You're asked, would you like a cup of tea in a certain general setting? Now, if you accept that, you might as well say, it is challenge response, but you must take into account a bigger situation. The bigger the situation is that you can take into account, the smarter the system will be in its response, the more fitting this response will be. So even if just the last shapes here are really exchanged, if the human and the system keep track of the previous history, then it is still going to be a challenge-response pair, but one which does pay attention to the general setting or situation by keeping a history. So the principle of challenge and response pairs does not need to be changed simply because you consider a history. Now, what happens if the system does not know at all how to handle a situation? If the situation is perfectly new to it? Well, then it can learn by imitation. And here I would like to outline how that happens. Let us say the system is challenged by this fluffy animal, and it really has no idea how to react on that. What do you do when you see that? It then rebounces that situation to the human. It just waits to see what will the human do. It doesn't do anything. It just looks at how the outer world will handle the situation. It rethinks it back. So in fact, now the human, because nothing happened with this fluffy animal, it's now the human to respond on it. And he eats it. All right, that's quite a terrible kind of reaction. But that is a possible reaction. And the system sees that the proper way to handle a new situation is to give a certain response to it. And by observing how is a situation handled, the system can in future also eat the fluffy animal. In other words, it learns by imitation. That is how imitation can be reflected into challenge-response pairs. Now, some people have asked, what happens when you do nothing, when you just wait? Well, to this one may say, waiting is also a kind of response. If you do nothing, if you sit still, if you just wait for something to happen, you are also replying in some way. Your inaction is in itself a kind of a reply and is to be treated in no other way than everything else subject to the challenge-response mechanism. Now, you may notice something interesting. I have not mentioned so far on what kind of information the system operates. And that is so on purpose, because what we have so far explored applies to any kind of information. If it is visual, auditive, text, or tactile, or anything. The principle of guessing a reply, learning a reply, and evaluating it, and finding further analogies and conclusions, can be applied to any type of input whatsoever. And if you see people who say that their artificial intelligence is going to handle visual input, but it must also be made to handle text and so on, they are transferring a problem of sensors into a problem of evaluation. That approach is, in my view, incorrect. Your system should be able to reason on anything in the same way. But how does reasoning happen? How does the system ever get information, and how does it ever put information into the outside world? For this, I have made this little scheme. You have two instruments. The first instrument is the sensor, and the second instrument is the actor. You see, in my view, the whole reasoning mechanism is fully automatic. You think simply because you have to. You can't really stop thinking. Even if you think about something else, you just change the subject of evaluation, but you still do evaluate. And the same way sensors and actors are automatic. Let us see there is green grass, you perceive it through the sensor eye, then automatically the thought of green will be generated. You don't choose to see the grass as green, but this input is automatic. And that is a thought. Green happens only inside your head. What the grass really sends out are just some light reflections. But what you reason on is what your sensor has placed into your evaluation mechanism. So, then actors are the opposite of sensors. A special thought is being processed, and it directly is coupled to a simultaneous action. For instance, you step somewhere. And when you're connecting these two processes of sensing to acting, you're going to establish interaction between a system and the outside world. Now, how can such a connection be established? I say by form of instincts. So, you're seeing something, it generates a thought, then that thought is somehow connected to output, and then you do something. This instinct, as I call it, can be used for further reasoning. For instance, you go somewhere because you see something, but you might also go somewhere because you hear it. And you might not only go there, but you might take it. For instance, you see your kid, you go to your kid. You hear your kid, you still go to your kid. You go to your kid and you take your kid on your arm. So, by having an instinct, you can actually, through further reasoning, create new connections between perception and action, which before that were unavailable to the system. Without instincts whatsoever, the system would only be observing things, but being unable to act on them because it has no idea how that thought should lead to any action whatsoever in any circumstance. It needs some principium from where on to continue derivative thoughts and arrive at the idea of how to act correctly. Now, following that, I did some experiments with the Arduino. What we have discussed so far can be formalized in the following way. The human, that is you or me, and the Arduino are going to interact by blinking lights. And the human is going to input a pattern of 3 lights to the Arduino, and the Arduino is going to output a pattern of 3 lights to the human. And that is again such a challenge response circle where the Arduino must guess its responses, and when the human says something, the Arduino can learn such a response. Input and output I am keeping extremely simple so as to make it easily understandable. The input happens through push buttons. 4 push buttons, which where each push button is also connected to an LED. This is just for the sake of clarity, so you see which button has actually been pressed. The LEDs are green, yellow, and red. And then there is the fourth push button, where the LED is, I call it anonymous. It is also of color red, but it has a special property which I will discuss in a moment. The output, like when the Arduino replies to you, is by activating three possible LEDs, a red, a green, a blue, and a green one. So red, blue, green is the possible answer to green, yellow, and red. In fact, these push buttons and LEDs are connected in the software through instincts, which I just discussed. So when you are thinking of something green, you will activate something red. When it is thinking of something yellow, it will activate something blue. And thinking of something red, it will activate something green. But what happens with the anonymous button? Well, it has no direct instinctive reply to it. The anonymous button is just being perceived but not directly connected to any kind of action. To learn a proper action for the anonymous button, the system must employ evaluation. It must learn that by analogy. Now, finally, I would like to show how these push buttons and how the output are actually wired. So you're having 5 volts lead to a push button leads to an LED, and the LED is then leading out on the one hand to one of the pins 5, 4, 3, or 2, and the wire is also split and goes to a 560 ohm resistor, which is connected to ground. That is for each of the inputs. And the output is one of the pins 6, 7, or 8 is connected to an LED. This is connected to a 220 ohm resistor, and that is connected to ground. So that applies for each one of the inputs and outputs which you saw before. In the next video, I am going to show how we are actually going to play with the Arduino and let it interact with us. Thank you.